So this lesson here really covers geometric theorems and theorems that you will see either you take pre-AP geometry or just on-level geometry. Here are some important theorems that I think you should really understand here for geometry. So the first theorem here it's known as a tangent angle really. So I have a circle here, right? And really I have a radius. So I have a radius here and obviously this is 90 degrees. And so we have like a tangent line here. So a tangent is really defined as a line that touches a circle at one specific point. So you're saying that this is that point where the line is touching the circle at, and it's always forming a right angle with the circle's radius. So if this is the radius, right, that tangent line is forming a right angle with the radius of the circle here. And so that's what the property really states. And obviously, how you apply this, you could form a triangle here, and how you know that the radius, this could be the altitude of this triangle. And again, using the law of sines and cosines, you can find this angle, which could give you the measure of your central angle, and based on your central angle, then you can find the area of this sector if you know the radius of the circle, because obviously if you determine the area of the entire circle and you times that by this x degrees divided by 360, right, you multiply that ratio by the area of the circle, you can get the area of this sector. Similarly, same thing with the circumference, right? So you can do many things, but that's the first theorem. So this is known as the tangent angle theorem. Again, it states that so you have a tangent, again, which is a line that just touches the circle at one specific point, and it always forms a right angle with the circle's radius here. So this is a right angle. Again, more like an altitude. This is more like a base, and obviously these side lengths will be equal. In a way, it's an isosceles triangle, if that makes sense. This angle being equal to this angle. So that's your tangent angle theorem here. The second one I really want to go over. Just show a visual representation of this. So you have a circle here, right? You have a circle here. So what this states is that if two tangent segments are drawn to a circle from an external point, then those segments are congruent. And obviously, this is applicable. For instance, if you have a kite, right? A kite, something like that. So it has these two consecutive sides that are congruent, and then you have this side and you have that side, right? So you have these two being equal and you have these two being equal. So that's how that works. But what this really, just showing you a graphical representation of this theorem, you have a center here. You're extending this, you have a right angle here, and then you have really just a line. And so you can say that this is just point A, or anything you want, and obviously this is point O, that it's your center, and then you have another one here. Again, it's that idea that this is a tangent line, right? So let me just draw this as something like that, right? It's going on forever here, so I wouldn't say exactly it's a tangent line here, because obviously this is more like a secant line. It's crossing the circle at 2 points, but this one, does look like a tangent line because it's crossing the circle, touching the circle at one specific point here. So we can say that this is G, right? And so this point over here is our external point. This could be N. And so what this theorem is saying, if two tangent segments, if the two tangent segments are drawn to a circle from an external point, then these segments are congruent. And so when I said secant line, it may be better for me to say a tangent line. And I think what happened here is that it's just because it's more like a sketch, I didn't show it correctly here, but it would be something like that. A circle, it would still be a circle, obviously. It would still be a circle, but we're still talking about a line that's tangent, and here, again, this line also being a tangent. So both of these lines are tangent to the circle, right? And they are being drawn from an external point, right, and they're being drawn to a circle from an external point, and these segments are therefore congruent. So you see that this segment from N all the way to G could be, I don't know, 8 centimeters, right? and if this is 8 centimeters, then the point from N to A, right, that segment is also 8 centimeters. So that's just another property you may want to keep in mind. Just reiterating it states that if two tangent segments are drawn to a circle from an external point, right, this is your external point, then those segments are congruent. So obviously you're looking from your external point all the way to the point where the tangent line is touching the circle, right? So this is 8 centimeters, this is also 8 centimeters. And something to look, because when I was talking about a kite, really, this is the radius, obviously the radii of the circle are congruent, and you know that this segment and this segment are also congruent. And if you think about this, you can rotate this figure and it becomes a kite, and then you can use the properties of a kite to further answer problems that deal with this theorem. And again, with the properties of kites, I have gone over those in my really first lessons that I had delivered at that time. So really looking at a kite, you can apply this theorem by drawing out the kite and then using the properties of the kite. So that's the second theorem that I wanted to go over. And now here comes the third theorem for this, or in this lesson that I'll be covering. And it's known, if you want, you can search up the name for this, but really, when I think of this theorem, I'm really thinking about a central angle and an inscribed angle. So I take a point, obviously this is a center, right? Take a point, and then I'm drawing two, really, because this is a center, so these are really the radii of the circle. And then I'm trying to really extend a segment from this point anywhere else on the circle, and then extending another segment from this point, it's on the circle, back connecting this segment. So the theorem states that the central angle is twice the length of the inscribed angle. This is your inscribed angle, and this is your central angle. So your central angle is 2 times your inscribed angle. You may be given something like, oh, the sector, I don't know, you may be given that this arc over here is 80 degrees. Well, this 80 degrees here, that's referring to this arc, really means that the central angle is 80 degrees. Therefore, this angle must be 40 degrees. And so it states that the inscribed angle is half the measure of the central angle. And so this does lead into another theorem. And so what that theorem states is that if you have a circle, you have a diameter, right, and you're connecting. So really you're saying that you have a right-angled triangle here. So if you have a diameter, right, again, this is a center, and then you're connecting, or you're extending 2 segments, right, from these 2 points, and you're joining those 2 segments at a specific point, right, something like that, then you have a right-angled triangle. And that makes sense, because really this angle over here is your central angle, right? It's 180 degrees, because this is a diameter, it's a straight line. And so if you're extending those 2 segments from these 2 points, connecting them here at this point, then obviously this angle formed here is your inscribed angle, and your inscribed angle will be half of your central angle, so therefore this is 90 degrees. And so that's another theorem that's derived from the inscribed angle theorem here that I've shown. So these are some geometric theorems that you should be knowing before you enroll in geometry. So thanks for watching.